Welcome back for part 2 of our section on properties of logic. In this section, we'll look at the 5 remaining fundamental properties of logic and how to prove them using truth tables. As a quick review from part 1, there are 8 properties of logic. If you haven't watched part 1, go ahead and do that now. In part 1, we show that the commutative property is true for conjunctions and disjunctions, that the associative property is also true for conjunctions and disjunctions, and 2 particular identity properties. We're going to move on to our 4th property, which is called the distributive property. Now, you've used the distributive property in algebra before, where you can distribute multiplication over addition. That's similar to, but not quite the same as the way the distributive property works for logic. In general, disjunctions and conjunctions can be distributed over a set of parentheses as long as the set of parentheses contains the other connective. So P and Q or R can be regrouped and distributed, and this becomes P and Q or P and R. So for example, statement P, you can order a hamburger. Statement Q, you can order fries. And R, you can order onion rings. The left side of our biconditional says you can order a hamburger and fries or onion rings. Fair enough. The right side of our biconditional is exactly equivalent and says you can order, another way to say this, a hamburger and fries or a hamburger and rings. Those are the 2 ways that you can state the same logic statement. Note though that this distribution occurs over the other connective. In this case, conjunction distributes over a disjunction. But it's also true that a disjunction can distribute over a conjunction. That is to say, P or Q and R is exactly the same as P or Q and P or R. So let's look at a case here that's a little bit easier to think about. Statement P, you have a reservation at the restaurant. Statement Q, you have the patience to wait until a table opens up. And R, you have the time to wait until a table opens up. So if you walk into a busy restaurant, there's a few different things that can happen. The left side of our biconditional says P or Q and R. That is to say, you have a reservation, or, if not, you have the patience and time to wait. In either case, you'll be able to eat. So the distributive property says we can now distribute that P over the Q and the R, and we end up with P or Q and P or R. That is to say, you have reservations or patience, and you have reservations or time. Now this one is a little bit less intuitive. In either case, if you have reservations, then fine, you're going to eat. But if you don't have reservations, then you must have patience and you must have time, in which case you'd also be able to eat. If you don't have reservations and you don't have patience and you don't have time, then it's probably not the right restaurant for you. Our 5th property of logic is called De Morgan's property. Disjunctions and conjunctions can be expressed through the other by using negation. This is not a very intuitive property, but it is a very important logic property. Here's what it says. It says if we have a P or Q statement and we negate that, we can distribute that negation, but it switches our signs to conjunction. So if we don't have P or Q, that means we don't have P and we also don't have Q. So let P be the statement you have some cash. Q means you have some coins. I think you'd agree that if you don't have any cash or coins, that means that you don't have any cash and you don't have any coins. If you don't have one or the other, that means you don't have one and you don't have the other. Negation distributes, but when we do, it reverses conjunction and disjunction. The same thing is true when we distribute a negation over a conjunction. If we don't have P and Q, it means we don't have P or we don't have Q. Again, P, you have some cash. Q, you have some coin. So if you don't have cash and coin, then you must be missing one. Either you don't have cash or you don't have coin. So we don't have both. We distribute that, switch from conjunction to disjunction. It means we don't have one or we don't have the other. De Morgan's property. So here's a practice problem for you to think about. Use De Morgan's property. What would be the equivalent way of saying it's not raining out and it's not windy out? You could use De Morgan's property to say that in a different way. Think about what that would be. Okay, if it's not raining, assuming that we let R be the logic statement that it's raining, and it's not windy, that's equivalent to say it's not, and we could put those two together in parentheses, but we'll change from a conjunction to a disjunction. De Morgan's property says it would be equivalent to saying it's not raining or windy. Okay, let's use a truth table to show this one case of De Morgan's property. We have two logic statements, P and Q here, and their associated combinations. To build the left side of this biconditional, we're going to need a P or Q and the negation of P or Q. There, that takes care of the left side of our biconditional. Now let's build the right side of our biconditional. We need a not P and a not Q column. From there we can build the entire right side of the biconditional, not P and not Q. And now we can see if our actual biconditional is a tautology. So to check for a tautology, we're just going to compare our left side biconditional column against the right side biconditional column. Since it's a biconditional, we need those entries to match in every row, and they do. The fact that this biconditional is a tautology proves that they are equivalent. And that proves De Morgan's property for this case. So in addition to the three properties that we've already seen, we can now add the distributive properties and De Morgan's property for each case. That leaves us with three more properties, each of which are very short. So let's take a look at those now. Our sixth property is the idempotent statement, and that just says if you have a logic statement in conjunction with itself, it's the same as having that logic statement alone. It's also true if you have that logic statement in disjunction with itself. It's the same as having the logic statement alone. So let P be the statement, you can eat salad for lunch. You can eat salad for lunch, or you can eat salad for lunch. Well, really all that means is you can eat salad for lunch. Even though this is a disjunction, it's really just the original statement P. And I think you'd see the same thing would be true if we replace this word with and. You can eat salad for lunch, and you can eat salad for lunch. Well, in the end, that just means you can eat salad for lunch. Our seventh property is the double negation problem, the old two wrongs make a right argument. That is to say, if you have a logic statement negated and negated again, it's the same as the original statement. So let's let P be the statement, you love cheesecake. If you negate that, you'd have, you can't love cheesecake. But if you negate it twice, you'd be saying you can't not love cheesecake, and that of course means we're right back where we started. You love cheesecake. And our eighth property are the contradiction and tautology statements. We kind of throw these together because even though they're different, they behave almost exactly the same. So, I'm a baseball fan. I'm from Minnesota, so I'm a diehard Twins fan, which also means that I just can't stand the Yankees. I'll become a Yankees fan when they get new uniforms and when elephants fly. It's a colorful way of saying I'm never going to be a Yankees fan. So, in terms of logic, if we have a logic statement in conjunction with something that's never true, then it can never be true. In other words, something could happen if something impossible also happens. Well, then it can't happen. Let's show that on a truth table. we have our statement P along with a contradiction. P could be true or false. The contradiction is always false. Therefore, P and C will both be false. And so the biconditional P and C with C compares this column and this column. Since both rows match, that's a tautology. It's always true. And so that proves this contradiction statement. The very similar tautology statement, P or T, when we combine P disjunction with a tautology, then that really just means a tautology. In other words, I'll be a Twins fan when they get new uniforms and when the sun rises in the east. Well, again, that's a colorful way of saying I will always be a Twins fan because the sun always rises in the east. This truth table, again, has P, but this time we have a tautology. P can be true or false. A tautology is always true. The left side of our biconditional is P or T, which is going to be true and true. And our biconditional statement, P or T equivalent to T. We're comparing those two columns, and of course they match. We have a tautology, and so we've proved the tautology statement. So that rounds out the last of our 8 properties of logic. Property 6 was the idempotent property, which shows that repeating the same statement with conjunction or disjunction is equivalent to the original statement. The double negation property that says if we negate a statement twice, it's the same as the original statement. And as we just saw, our contradiction and tautology statements. So here's one more practice problem for you to do before we bring this section to a close. I would like you to create a truth table to verify the logic statement on your screen. It's a bit of a messy one, and I would like you to identify which property we're using here. So pause the video, take a minute, create the truth table that shows that to be true by creating a tautology in the last column to prove the logic statement, and unpause the video to see the solution. Okay, in this case we have P, Q, and R and their associated combinations. So let's start building the left side of this biconditional. We need a Q and R column. You can verify that Q and R will look like this. And so now we can build the entire left half of this biconditional. Now let's build the right side of this biconditional. We'll need a P or Q column and a P or R column. And now we can make a column for the entire right side of the biconditional. And that allows us to verify the entire property. We're checking the biconditional statement of this column against this column, and every row matches, which proves this is a tautology and verifies our identity. So our last question then, which property is this? Do you recognize it? Can you tell which property we saw in this section says that that biconditional is true? Well, I'll bet you did. P is being distributed over Q and R here. And when it's distributed, the disjunction is distributed over a conjunction. This is the distributive property. Okay, so that wraps up this section. You should now be able to recognize the 8 properties of logic and be able to use them and prove any one of them using a truth table. So the assignment for this section is a little bit different. Only part of it is on Blackboard. Part of it will be submitted directly to me since these truth tables are a bit tricky. Make sure to follow the instructions for the assignment for this section given in Blackboard, and as always, let me know if you need help.